Okay, this video is going to cover the notes for days 44 and day 45. I think we can do everything in one video instead of spreading it out over two. The title for the section is Bases Other Than E. And so while we know to take the derivative of e to the x and get e to the x, if you have a base other than e, you can actually rewrite this other base a as e to the natural log of a times x. If you simplify that, you wind up with a to the x. But the reason why you'd want to write it this way is when you take the derivative of this is just all of this stuff times, by chain rule, the natural log of a. And then all this is a to the x. So the result right here is this here. The derivative of a to the x is a to the x times, by the chain rule, the natural log of a. Okay. Same thing if you have a function as your exponent, you just do the extra step of doing the chain rule on whatever function is the exponent. And then to take the derivative of log base a of x, you could follow this proof here. Using change of base, log base a of x is the same thing as the natural log of x over the natural log of a. We know that the derivative of the natural log of x is 1 over x, so it's 1 over natural log of a times 1 over x, or 1 over natural log of a times x. And then chain rule extension is right there. So we'll be using those properties in the examples in the following screens, but a quick summary of what happens for all kinds of different base and exponent combinations. If both the base and the exponent are numbers, then the derivative of any constant is 0. If the base is a variable, then the power rule says drop the exponent down and then subtract 1 from the exponent. So the derivative of this would be e times x to the e minus 1. The derivative of e to the x is just e to the x. And then if you have both a variable in the base and the exponent, then you're going to do natural log differentiation to figure this one out. So you're going to take the natural log of both sides. On the right side, the natural log of x to the x means the x exponent falls out front, and you have this statement here. Taking the derivative of natural log of y is 1 over y, but by chain rule you need a y prime. This is the product rule, derivative of the first times the second plus first times the derivative of the second. That simplifies to the natural log of x plus 1. And then when I bring the y up to the other side, natural log of x plus 1 times the original x to the x. So that's that statement there. Other property summaries, if you have an argument that can be simplified into some sort of power of the base, like this situation here, 125 is 5 cubed and the denominator is 5 to the negative 3. The base and the exponent are the same, the base and the argument are the same. The exponent falls out front, and then when you have log base 5 of 5, that's 1. So that statement simplifies down to negative 3. There's two different ways of doing this. A similar situation is I see that 3 is the base for both of these things here. So I could either change forms, set this question equal to x, 27 to the x equals 9, get the same base. 27 is 3 cubed, so 3 to the 3x equals 3 squared, and solve for x equals 2/3. Or you could take and do change of base, okay? Log base 27 of 9 could be written as log base 3 of 9, log base 3 of 27. If you take and change 9 and 27 into 3 squared and 3 cubed, exponents fall out front. These remaining parts either cancel out or log base 3 of 3 is 1, but you wind up with 2/3 either way. So we're going to walk through 3 word problem examples in the next 3 screens. Rate of inflation is 5%, and if you take the cost of something and factor in inflation, you'll get this kind of a function. The cost is the original amount or the principal times 1.05 raised to the t. So price of an oil change is presently $24.95. Estimate the price in 10 years. $24.95 goes in for P, 10 goes in for T. Substitution, you get a predicted value of 40.64. Find the rate of change for C with respect to T when T equals 1 and T equals 8. What's the derivative? P is a constant. So when I go to take the derivative of this, P is a constant, it doesn't matter. This base is not E, so I'm going to remember that the derivative of this exponential function is 1.05 to the T times the natural log of 1.05. So the derivative is right here. Constant times natural log of 1.05 times the original exponential statement, 1.05 to the T. Substituting 1 and 8 into these produces statements that are in terms of P. So after T equals 1 year, you're going to get 0.051 P, and after 8 years, it's 0.072 P. And then finally, verify that the rate of change of C is proportional to C. So the rate of change compared to the original function, put the rate of change function up top, put the original function on the bottom, Lots of stuff cancels out. The only thing that's left behind is a constant or a number. So there is a constant of proportionality of natural log of 1.05. So to figure out how to take the antiderivative of a base for an exponential function with a base other than e, I'm going to start with the derivative statement and undo the derivative. So if I start with the derivative of a to the x is the natural log of a times a to the x, and I'm going to take the antiderivative of both sides. The antiderivative and the derivative cancel out. So on the left side we have a to the x equals the antiderivative of the natural log of a can be rewritten as ln a antiderivative a to the x because the natural log of a is just a constant. And when I move the natural log to the other side by using division, what we wind up with is the antiderivative of a to the x dx equals 1 over the natural log of a times a to the x. Second word problem, when a person takes a 100 milligram tablet of an asthma drug, the rate at which the drug enters the bloodstream is predicted to be this. So this is an exponential function that's a rate. And again, anytime you are given a rate function, you should be thinking about the net change theorem because the antiderivative of a rate is an amount. If the bloodstream does not contain any trace of the drug when the tablet is taken, determine the number of minutes needed for 50 milligrams to enter the bloodstream. So here's our rate function. At time equals 0, there was no drug in the body. Find the time when the amount equals 50. So the antiderivative of rate is amount. Bring the constant 5 outside. You need the antiderivative of this, which is 1 over the natural log of 0.95 times 0.95 to the x, evaluated from t to 0, and it equals 50. Solve. Substitution and solve. I factored out 5 divided by the natural log of 0.95 and wound up with 0.95t minus 1 equals 50. Bring 5 and natural log of 0.95 to the other side. 50 over 5 reduces to 10. Add 1, and then now change forms. Log base 0.95 of this statement is t. Substituting all that into a calculator, you get 14.024 minutes. So for the last example, which is going to take 2 slides, we're going to investigate exponential decay of substances and exponential growth of money. Exponential decay occurs when you start with a set amount of something, say 1,000 milligrams of some sort of substance, and after 10 years, you wind up with half as much, which is 500. And then after another 10 years, you wind up with half of that, 250, and another 10 years, half of that, which is 125. If you keep track of the rate of change, the decrease, the change in the amount over the change in time. This was a decrease of 500 units over 10 years, so negative 500 divided by 10 is negative 50. The next 10 was a decrease of 250 divided by 10, which is negative 25. The next decrease was down by 125 divided by 10, negative 12.5. If you instead started with 500 units of that substance, cut it in half, 250, 125, 62.5, divide each of those by 10 to get the rate of change, negative 25, negative 12.5, negative 6.25. What's happening is the decrease rate depends on the amount of substance. Here's an exponential decay curve. Okay, the decrease rate, the slope of the tangent line, depends on how much substance you have. The decrease rate is changing. Fairly negative, not so negative, getting closer to 0. So the decrease rate depends on how much remains. For money, if you start with $1,000 invested at 5% compounded on a regular basis, after 1 year, you would have $1,000 times 1 for the original amount. You get to keep your $1,000, and then you're going to tack on an extra 5% of that 1,000 in interest. So after your first year, you have 1,000 times 1.05. As you go into the second year, that balance times 1.05, get to keep the original amount, which is the 1, plus another 5% tacked on, gives you this statement. So after 2 years, you'd have 1,000 times 1.05 squared. The pattern continues. After 3 years, the 2-year total times, again, 1.05 gives us 1,000 times 1.053 to the third. So after n years, you have $1,000, 1 plus 0.05 raised to the n. If your compoundings occur more than once a year, you take and modify both the interest rate and the number of times that you're compounding. So for example, something that's compounded twice a year, you're going to take that 5% and cut it in half each time you do a compounding. So half of 5% is 2.5%, but then you're going to double the number of times that you compound. So it's going to be 2 times the amount of time that you have. Continuing that pattern, if you have something that's compounded monthly, monthly is 12 times a year, your 5% is going to get split into 12 equal percentages, but then you're going to compound it 12 times per year. So the general form is you start with the principal, you take your interest rate, divide it by the number of compoundings per year, and then you take the number of years t and multiply by the number of compoundings per year n. So that's the general form. But most banks don't compound your interest at a regular interval. They compound your interest continuously, which means every fraction of a second you get more interest. So what happens if n approaches infinity? That's called compounding continuously. In order to modify this formula, we're going to do a slight math trick. I'm going to replace r over n with a statement. I'm going to let x equal n over r. So that's not quite matching this. What's happening is that's the reciprocal of x. So if x is n over r, then r over n up here is 1 over x. And the other thing I'm going to do is I'm going to take this n and say that n equals x times r. Where did that come from? If I take this substitution and solve for n equals x times r. So replacing r over n with 1 over x and n with xr, I get this statement here. And the reason why we want that statement here is that this quantity right here is a very famous math quantity. We'll prove it later, but if I let x approach infinity, we said that we're going to increase the number of compoundings to infinity. If I increase n to infinity, that's the same thing as letting x increase to infinity. If n is infinite, then so is x. The limit of this green highlighted statement as x approaches infinity, written over here, is e. We'll prove this later in the year, but 1 plus 1 over x raised to the x as x approaches infinity is e. So everything in the green highlighted section here gets replaced with e, and the formula for continuous compounding is a equals p times e raised to the rt. So that's the formula for continuous. This is the formula for regular compoundings. Okay, that's the notes for days 44 and 45.